In video 71 of Tensor Calculus, we'll begin our analysis of the covariant derivative as it relates to surface manifolds. Now in this video, we're going to restrict our discussion to those vectors that lie in the tangent plane. In the next video, we'll extend the analysis to the more general case. Back in video 28, we introduced the covariant derivative by taking the partial derivative of a vector with respect to our coordinate zj. Well, today we're going to investigate the covariant derivative as it relates to surface manifolds. And to do that, we'll take the partial derivative of our vector t with respect to our surface coordinate s beta. Now, for now, we're just going to limit our investigation to tensors that lie in the tangent plane. So we're stipulating that vector t here lies in the tangent plane. And because it does, we can represent vector t as a linear combination using our surface coordinates. So we can express our vector t as t alpha times s alpha like this. And of course, remember this is something we can only do if the tensor or the vector lies in the tangent plane, but of course that's what we're stipulating. Okay, so of course I have to proceed with the product rule. All right, well, it's at this point in our video 28 that we took a little side investigation of this new term right here, the partial derivative of our basis vector with respect to our coordinate. But for our surface coordinates, we did all of that in videos 68 and 69. So all we need to do now is to substitute what we did in video 68 for this expression. Okay, so what I'm going to do now, instead of using this term right here, I'm going to use the result that we got back in video number 68. All right, so what you see here is that this expression right here is what we got for this expression in video 68. I've just made a direct substitution here. Okay, so the next step then is to expand this out and to distribute this factor of t alpha into these two terms right here. Okay, now as I distribute t alpha into this first expression, I want to reorder the terms. So I'm going to put gamma first, and then t next, and then our basis vector s last. And I also want to rename some of the indexes here. Now the goal is that I want this basis vector to be s alpha because I want to be able to factor that out in a minute. So first thing I need to do is to rename the index omega to alpha. So this will become alpha, and I've got to change the omega in this position to alpha as well. Okay, and then what else will we do? I will switch the order of the terms here, alpha, beta, and I'll put beta first, like this. And then since I'm using alpha here, I can't use alpha for this particular dummy index, so I'm going to change it to omega. All right, so all I've done, I've distributed the term, reordered the factors here, and renamed some indexes. But in the process, understand that this expression is the same as what we get if we just distribute t alpha into the first term. And then, of course, I have to carry on with the second term as well. So I'm going to distribute t alpha to the last term. So now what we can do is to factor out s alpha here. So if I take this out of the expression, then what's left will lead us to the definition of what we call the surface covariant derivative. And with this new definition, we can now rewrite our expression here this way. We'll have the partial derivative of our vector t with respect to s beta is equal simply to this new object, our surface covariant derivative of t alpha times s alpha. Remember, we factored this out a minute ago. So s alpha is not part of the definition. And then the last term, t alpha times b alpha beta in hat. Okay, so what have we got here? Well, the first thing you're going to notice surely is that this form right here looks exactly like the definition we came up with in video 28 for the covariant derivative. And indeed it is. It's exactly the same form. So our definition of the surface covariant derivative, at least for vectors that lie in the tangent plane, is exactly the same as our standard covariant derivative. So we don't have to make any adjustment at all to the definition. But what does happen is something that is similar to what happened in video 68. And that is that we went through the analysis, we came up with a new term out here. If you'll remember, when we did this for the covariant derivative in video 28, we came up with an expression here that looks like this. And indeed, this is the expression that would be correct for a simple plane. So as long as we're dealing with a Euclidean space, this is all we need. But when we branch into a surface that is curved, we run into this new term right here. So it's very similar to what happened in videos 68 and 69. And for the same reason. The reason is that when we take this operation, this partial derivative of our vector t with respect to s beta, even though the vector itself lies in the tangent plane, it's not necessarily so that the partial derivative remains in that tangent plane. In other words, as we take the partial derivative here, what we wind up with is a result that has a surface projection and a normal projection. So the operation of taking the partial derivative introduces a component in the normal direction. And of course you recognize this as the form of a vector that lies in our tangent space that may be general and points in any direction. So the comment here is very similar to what we said in video 68. The definition of our object remains the same, but its application is modified to extend to this extra term here. Now notice how consistent it is. We said that if a surface is actually a plane, then our curvature tensor here is going to be 0. This term drops out, and we're left with this, which we know already is the correct answer for a plane. So what we've done here is to generate a definition and application that is generally applicable, and the result for a plane is simply a special case of the more general expression we came up with. Okay, so let's move on now to do the same thing in respect to this works when we're dealing with a vector component that is a contravariant vector component. It has an index in the upper position. So let's repeat the exercise using a vector component that is a covariant component in the lower position. All right, we're going to go through the same drill, only this time we're going to use a linear combination with a contravariant basis. So we'll have the partial derivative with respect to s beta, and the linear combination is going to have a covariant component and a contravariant basis like this. And of course we have to start as before with the product rule. All right, so next we're going to make the substitution for this term with what we derived back in video 69. So this expression is the same as this one. Okay, next we will distribute this term here into each of these, and in the process I'll do some rearrangement and some index renaming. Okay, notice that I have renamed the omega index here to alpha here and here, and I've renamed the alpha index here and here to omega. Okay, and the purpose of that is that I want to be able to factor out this factor of S alpha in just a minute. Okay, so that lets us now define the surface covariant derivative for a covariant vector component. And finally, we can express our expression up here this way. the partial derivative of our vector with respect to s beta is going to be equal to our new object here, again times our basis vector because that's not part of the definition, and then the remaining term out here, T alpha contracted with B alpha beta in hat. Okay, so you can easily see that all of our comments from before carry over to this form as well. This expression right here is the expression we derived, I believe, where was it? Back in video 32, we derived an expression for the covariant derivative of a covariant vector component, and it's exactly the same form. But again, here, because we apply it to a curved surface, we get this new term. This is what we would expect for a plane or Euclidean space, and we get this new term because our space is curved. And again, if this is equal to 0, then our more general form here resolves back to the more specific case for a plane. So everything we said before carries over here as well. We have a expression here which results in a surface projection and a normal projection. It's a vector that may point in any direction. Okay, well, now because each of these covariant derivative forms are the same as what we derived for Euclidean spaces, it makes a lot of sense that the properties that we derived for these objects in those previous videos would carry over to curved surfaces. And indeed, it's true that almost everything we derived and analyzed about these operators continue to be true even though we have a curved surface. However, there are two very important exceptions. So I want to wind the video down by showing you those two very important exceptions. Back in video 37, we discovered that the covariant derivative of our basis vectors, at least in Euclidean space, is equal to 0. We say that our basis vectors possess the metronylic property. Well, we're going to discover that the same is not true for the basis vectors on curved surfaces. And to see why that's so, let's just apply our basic definition. So if we're going to take the surface covariant derivative of our basis vector S alpha, we'll have to start with a partial derivative, as always. So we'll have the partial of S alpha with respect to S beta. And then because the index is in the lower position, we need a negative term, gamma, and then the indexes are both in the lower position, down here, and we'll have a dummy index here with S omega like this. Okay, so next what we'll do is we'll make a substitution for this term with what we derived in video number 68. So let's do that. Okay, so this expression right here, these two terms, are what we derived in video 68 to be the equivalent of this. Okay, and you see right away that this term and this term cancel out, leaving us with this. So our covariant derivative here is not equal to 0, but it's equal to this. So the covariant derivative of our covariant basis vector is this. It's not 0, but it's equal to this term right here. Okay, so let's do the same thing for the contravariant basis vector. Again, we just apply our basic definition. So the covariant derivative of S alpha in the upper position this time, again, it starts with a partial derivative. And this time, because the index is in the upper position, we'll have a positive term with gamma. And here we have one free index in the upper position, one in the lower, so our free indexes are here and here, and our dummy index this time is this way. Okay, so now we will go back to what we discovered in video 69 for the equivalent expression for this. So this time, these two terms together are the equivalent of this, as we discovered in video 69. So again, we have terms that canceled out, and we're left with a non-zero term here. And that means that our covariant derivative of our contravariant basis vector looks like this. It's got a a non-zero term here. Okay, so what does this mean? Well, as we pointed out in video 37, if we had an expression like this where we're taking the covariant derivative of a linear combination such as TI-ZI like this, because of this metronyllic property right up here, that's the same as simply taking the covariant derivative of the vector component times our basis vector. In other words, we can just take this basis vector right here out of the parentheses. We don't have to apply the product rule because the covariant derivative of zi is equal to 0. So this is a convenient relationship because of the metronyllic property. Well, because of these relationships, we can't do the same thing in surface geometry. So if I were taking the covariant derivative, surface covariant derivative of a linear combination T alpha S alpha like this, I can't just take the basis vector out. So this is not equal to the covariant derivative of T alpha times S alpha. To perform this kind of operation, we're required to use the product rule to expand it out. So we lose this ability because of these relationships. Okay, well, what about the other metronyllic elements? You know, in other videos, we discovered all of these relationships, that the metronyllic property extends to our metric tensors, to the delta factors, and to our Levi-Civita symbols. Well, what about surface geometry? Well, as it turns out, we do not lose the metronyllic property for curved surfaces. So all of these properties are retained. It's only these two that we lose. All of these remain the same. Now you can convince yourself of that if you go back and look at videos 38 and 51. That's where we derived all of these things. And you'll find that all of the derivations that we did there did not have any dependence whatsoever on the space being a Euclidean space. So all the proofs and derivations that worked here also work for all of this. Okay, now that of course means that because of this relationship, that means that we can use our metric tensors to raise and lower indexes across this operation, just like we do over here. Now for the delta function, that means that we can use this relationship to absorb indexes across the covariant operation. And it applies here as well. And of course we can move the Levi-Civita symbol inside and outside the operation at will, whatever is most convenient. Okay, so I said that there are two exceptions regarding the covariant derivative in curved surfaces, and this is one of them, the fact that we lose our metronyllic property for our basis vectors. But there's one other, so let's go look at that. Back in video 36, we derived this relationship. We said that the covariant derivative is commutative. That is, if we apply the covariant derivative with respect to I, then j, we'll get the same answer if we take it with respect to j first, then I. So the difference of these two is equal to 0, and we say that the covariant derivative is commutative. But we also pointed out that that's only true in flat spaces. And if you remember how we derived this, we said that the covariant derivative in flat spaces would be simply the partial derivative if we were using an affine coordinate system. And we know that the operation of taking two partials in an affine coordinate system, that is commutative, so this would be equal to 0. And since it's true for affine coordinate systems, and since this is a tensor relationship, then we know it's true for all coordinate systems. Okay, but we cannot use that argument in curved surfaces because we cannot use an affine coordinate system. So the result is that the covariant derivative, the surface covariant derivative, is not commutative for curved surfaces. Now, it turns out that the fact that this is not commutative leads us to a tool that we can use later on to quantify what's known as the intrinsic curvature of the space. So we're not going to say any more about it now, but we'll have a number of videos that take us down that road to show how we can derive the intrinsic curvature of a space using this relationship. For now, just recognize that the surface covariant derivative of a curved surface is not commutative. And with that, let's end the video with a review. The main takeaway for this video is that when we're dealing with vectors that lie in the tangent plane, then our definition for the covariant derivative, this surface covariant derivative, is exactly the same as you'd see it for a simple plane, or for any Euclidean space for that matter. We don't need to make any changes or modifications to the definition of the covariant derivative as long as the vectors lie in the tangent plane. However, when we use the covariant derivative as part of the operation of finding the partial derivative of a vector, we do have to make some adjustments. You'll remember that if we're dealing with a simple plane, then the partial derivative of a vector would look just like this and this. But when we're dealing with a curved surface, we see that there's an extra term that shows up in each case. So what this tells us is this, that although the vector itself lies in the tangent plane, the partial derivative, which will of course be a vector itself, does not necessarily lie in the tangent plane. We have not only a surface projection here, but we have a normal projection here. So the resulting vector of this operation may point in any direction and not just in the tangent plane. Okay, but because our definition has not been modified, it's the same definition as for Euclidean space, then most of the properties of the covariant derivative carry over to curved surfaces. There are, however, two very important exceptions that we talked about. The first is that we lose the metronylic property for our basis vectors. So for flat surfaces, or such as a plane, this operation would result in 0. But here on a curved surface in general, we do not get a 0 result. We see these terms as a result of taking the covariant derivative of our basis vectors. Okay, and the second exception is that we lose the commutativity of the covariant derivative. The order of performing two covariant derivatives does matter. So taking it with respect to alpha then beta is different from taking it with respect to beta then alpha. And as I mentioned in the video earlier, we're not going to say any more about it than this. It's not equal to 0, and we'll use this later to establish a quantitative value for what we call the intrinsic curvature of the space. So finally, let me remind you that these are now the general results for surfaces. If we're dealing with a simple plane, then our curvature tensor is equal to 0, and this term would drop out, giving us the result that we already know is true for a plane. Likewise, these terms would drop out, giving us 0, and we would recover the metronylic property for our basis vectors if we're dealing in a flat space. Likewise, down here, if we're dealing in a flat space, we would be able to apply an affine coordinate system to this, and the result would again be 0. So what we've got is a general result here that includes the plane in it as a special case. And let me remind you finally that everything we did in this video was for this restriction. We were dealing with vectors that lie in the tangent plane. In the next video, we'll extend our analysis to include vectors that do not lie in the tangent plane.